All right. That's a good idea.
Yeah, take your time, never show.
So I was going to the other building, came across, I'm sure people probably went at 3 hours.
My experience is.
Yeah.
I was trying to find it. Like, yeah, it's a big.
So it's like 106, so it's in the third. Yeah. Yeah, that charges. Man.
Just away from the top.
Wait, take. You're right.
The reason I covers my everything. Yeah. And
And see, I think no.
Yeah, not around. That one's good.
It's not particularly. We get out of everybody.
And here. Yeah.
Where's it?
Yes, you might extend.
I don't know, I think these guys have been preserved like plants. Yes, well, yeah.
Anyways, has another.
No.
And then, no. Yes.
All right, Travis, Bobby, are we all good on your side? Ready to go?
Yep, everything's coming on in.
Great. All right, we're going to get started. Thank you for being here early in the mornings for our AGN SIG session. I'm Erin Hicks, one of the co-chairs, along with Vivian Yu of the Science Interest Group on AGN. And before we get started, I just wanted to, for those of you who might be new to this group, first, we'll have a QR code soon, so you can add yourself to the email list if you haven't done so. I'm going to just give you a little bit of a layout of the purpose of this group. So it's kind of twofold. Our view, we're here to bring the community together to promote, collaborative efforts towards advancing AGN science. Great. The other part of that is that we're here to help interface with NASA. NASA wants to know about what the community is thinking, our needs. And so this is our one route for us to be able to have our voice heard and to be able to say, this is what AGN science needs. This is what our community needs to be able to be successful. So we take that role pretty seriously, especially as we're leading into the next decadal survey. And so you'll see there's a lot of discussion around that. So before we proceed, I just wanted to mention, how to advance slides on my own computer. Just a little slow. Okay. Before I move into our wonderful group leadership council, I'll say that we are taking a risk to be on Zoom. So should we have somebody join who should not be joining, we will quickly cut off the Zoom connection. And for those of you who are online, we'll communicate out another link, probably Teams link. So prepare for that just in case we have that unfortunate event. But let's fingers crossed. Hope that we're going to be fine. So look for communication if we have an issue. All right, so Vivian, you and I took over as co-chairs about a year ago. We've recently been joined by this wonderful group of folks. So we have Mingy also in the room with us, Vivian's in the back, and then joining us online with Travis Fisher, Annika Goyle, and Lottie Patel, and Peter Maxim. So this enthusiastic group has great plans for the year. So I'll jump into that. And I also want to just take a moment to say Vivian Yu is shifting over to being a chair of the HAP World's Science Interest Group. So she's going to be leading us, but thank you for all of your efforts. It's been wonderful. All right, so before jumping into today's discussion and presentations, I want to just sort of advertising of our events that we have planned for the coming year. So we've planned roughly monthly events. Obviously, we're going to add a new series, Spotlight series. We're going to kick that off on January 27th with Namrata Roy and Lulu Zong. We'll be presenting recent results that they have. And so something that's always been a theme with our events is a lot of community discussion. And so this series will be similar. We'll have a focused presentation of the results to be shared in a 15-20 minute presentation, and then 10 minutes of discussion on each of those presentations. So look forward to that. We are also planning to continue our vision series, which has a little bit of a different angle to it in that it's a discussion on a broader topic, where we're at, what we need to be able to move forward with those big science questions. And so we hold that roughly quarterly. And so we can look forward to the first one in February. So our events are typically the third, sometimes fourth Tuesday of the month. That depends a little bit on speaker availability. We try to be flexible. And we're also adding this year a spring dissertation jamboree. So for those of you who are defending either this past fall or in the spring, we're hoping that you'll join us and share your work with your thesis during this event. So if you're not yet on our email list, please join that. You can access it through our website and the QR code there, and we'll have an announcement about that soon. So if you know folks who would be interested in this event who may not be in the room, please let them know. Look forward to their joining. Also, we'll mention We have years worth of events that are posted on the website, so please do join the email list, but also just go to the website, browse through all the great presentations that we have from the past. We also have new this year something called AGN Coffee. So this is geared towards early career folks. So there's been a new Discord server set up, so please join that, and through that mode of communication, there will be an announcement about events for those early career folks. And again, this will be in some fashion communicated by emails, just hot off the press. So we'll get this information out, and please, if you are on the email list but no others, please share it with them so we can reach a broad audience of early career folks. So we plan to meet monthly, talk about research, and so on. All things early career. All right, so that brings us to our session for today. But I wanted to start us off with where we were at last June when we had a similar Splinter session. And this is what the outcome of that discussion. We had a discussion about what the decadal process looks like, and then there was ideas put forward on the shared slide of white papers that we should start thinking about. And so, there's a lot of great things on here. I think all of this should be pursued. We could talk about the merits of each one of them today at length. But I wanted to kind of change our focus a little bit. You see that there's a lot of mention of funding. We still need all of that. You can imagine in June, we were kind of just coming to grips with our new reality at the funding front. And then there's also a lot of things here that are really great about capability, what we need to be able to do the next big steps in our next big science questions that we have in AGN science. But what I think we really need to do, and what we'd like to try to get us to focus on today, and which is consistent with what messages you've probably heard if you have attended the COPAC sessions over the weekend or any of the NASA sessions yesterday, particularly the one that talked about preparing to the 2030 decadal, is for us to focus on what are the next big science questions, not on how we're going to get there, but where do we need to get to. And so today's discussion, we're starting out with some great presentations that give us some highlights of where we're at now, what we need to we start thinking about to be able to advance those particular areas of AGN science. And then we're going to go into a discussion to think about, okay, what can we achieve now with what we know our capabilities are going to be in the near term, next few years. So what science questions do we think we're going to be able to address with what we have now? And then moving forward, what are the next big science questions that are going to be driving our field in the 10, 15-year time frame? And that puts us with the science questions we would want to push forward to really say, this is what AGN science needs, what our field needs to see in the decadal survey to be able to take those next big steps in advancing and understanding the importance of AGN, what their contribution is to shaping the universe into what we see today. So think, aspirational. I think we heard this yesterday. And in the NASA session, the decadal survey in many, many ways is an aspirational document. We want to be thinking big about what those science questions are and not limit ourselves by realities we may face on a funding front or other limitations. And then once we have those big science questions, then we can go to what does it take for us to get there? And then, those discussions follow. And a lot of that is right here. We've got a lot of good ideas on here. So you keep that in mind, and what kind of new science, these capabilities, more funding, what would that provide for our community? But hopefully we can get those big science questions down first, and that really can be what drives. All right, I'll hand it over to Minnie, who's going to invite our wonderful speakers.
Okay, this is me. So we have great speakers today. The Dr. Michelle Revalski from physics and from the STScI, and also Professor Tiffany Lopez, and from Michigan Tech, and also the Jianwei from the University of Arizona. So every speaker will have 12-minute talk with 3 minutes Q&A. So I will just continue from Michelle's and going to Tiffany and going to Jianwei's. So I will start. And so, should I go into it?
All right, good morning, everyone. Thank you for being here. I'm Revalski from Space Telescope, and I'm really excited to kick off the session today, thinking about where we've been, where we're at, and where we're going in trying to study AGN, specifically in the realm of trying to unlock really precise AGN outflow energetics with spatial result modeling. So kicking it off with the biggest picture view, if we look at giant simulations of the universe, such as Illustrious here on the right, we start at very high redshift, large dark matter halos, material collapses down, we form galaxies. At the center of those galaxies, we have supermassive black holes, and those supermassive black holes begin accreting material, feeding on it, and injecting an immense amount of energy out into their environments. So we can see here we have these little explosions of material going off as we move closer and closer to the present day. These are our active galaxies. These are our active galactic nuclei. So we know that supermassive black holes can inject an immense amount of energy into their surroundings that can alter almost every scale of the observable universe. So it may affect how the supermassive black holes are growing, their relationships with their host galaxies, how much gas is being evacuated in different phases. It may trigger or deter star formation. So this is really critical to understand for a variety of fields. Now, of course, this is difficult because it's a very multi-scale and multi-phase problem. We're going from the scales of supermassive black holes all the way out to galaxy clusters. And in order to get a deep understanding, we really need to trace basically every gas phase, molecular, neutral, ionized, radio, in order to get a deep understanding. And so in order to do this, we want to have really precise mass outflow energetics. We need to measure the masses and the velocity of these outflows in order to calculate key properties like the mass outflow rate, the energy outflow rate, and the momentum outflow rate. And this is really critical to do both observationally and theoretically hand in hand, because we need to break degeneracies between a bunch of different parameters. If we look at the very end of this illustrious simulation, we have a universe filled with hot gas everywhere. But as we heard in a really nice talk from Scott yesterday, there's a lot of knobs that you can twiddle in the subgrid physics here. And if we look from the previous generation simulation and we fade to the next, we can see that things have changed dramatically, even just in the course of a few years. So we really want to get these properties locked down observationally so we can tackle it from both sides. So as we said, our main goal is to get very precise outflow energetics. We want to measure it at high spatial resolution for a variety of gas phases, and then compare them with observable properties to understand the influence of the AGN on its host galaxy. Now, kind of the challenge here is that many of these measurements in the past have generally been roughly kind of global, usually unresolved, having a single measurement of the mass outflow rate for a single galaxy. And it's very difficult to get tight constraints on the mass, which ultimately relates back to what is the density of this gas. And so I want to share some of the work we've been doing across a couple of studies in the last few years to get really precise mass outflow energetics for the narrow line region outflows in nearby Seyfert galaxies. So these are moderate luminosity AGN with ionized gas spanning from basically a parsec from the supermassive black hole out to kiloparsecs of gas. So over here, on the right, we have NGC 4151, one of our favorite galaxies to study. If we zoom in from the ground-based view to HST, we can start to see an immense amount more detail. We can really resolve individual structures. And if we zoom in once more, we can actually see these hot ionized outflows glowing in this blue-white emission. And so this non-Marsden image, this is real HST imaging, and that's what we're using for the majority of our study. So hidden down in the center, we have our supermassive black hole, pumping out an immense amount of energy into the galaxy. It's ionizing this gas, exciting it, and driving it away from the supermassive black hole. From the imaging alone, we can see this is anisotropic, it's clumpy, it's complex. Imaging gives us our first half of the puzzle, and of course, spectroscopy gives us the other half. So if we use an HST long slit spectrum and we isolate the oxygen-3 emission lines, we do see red shifts and blue shifts consistent with rotation, but we also see much higher velocities of several hundreds to several thousand kilometers per second, which is indicative of gas being blown toward and away from their line of sight in this kind of biconical geometry. So with these studies, we set about studying a number of galaxies. So here's the first half dozen we studied from nearby Seyferts, kind of low luminosity QSO2s, a few of our favorite galaxies. And first I'll highlight what we did to get really precise outflow energetics. So here we have an O3 image of one of those targets, and on the top we have an example of a spectrum and the derived kinematics. So our first step is to go ahead and extract an HST spectrum at each distance from the supermassive black hole, fit the strong O3 lines to differentiate outflow versus rotation, and basically get what is the outflow velocity at each position. From there, we have a very wide wavelength coverage of our HST spectra, all the way down from the near UV to the near IR. And we have something like 30, 35 emission lines in some cases, from things like neutral oxygen all the way up to iron 14. So we have this huge range in physical conditions located from these very small extracted regions. It's like parsec to several parsec physical scales. So the key is we need to be able to match all of these emission lines in order to get a full understanding of what the physical conditions are and ultimately what the gas masses are. So for that, we're using multi-component cloudy photoionization models. This is an example of some of the grids here, looking at oxygen 2 on the left, O3 in the center, and a higher ionization like iron 7 on the right. And we're looking at it as a function of ionization parameter and density. And so we talk a lot about ionization parameter, right? It's the relative number of photons to atoms. So higher ionization parameter, more highly ionized gas. And so we have things that form at very low ionization parameter together with things that form at very high ionization parameter at the same physical location, which tells us that we have a huge range in density as we look at these outflows. So we create these multi-component models that basically sum up all the emission normalized to H beta in order to match all of the emission line ratios that we see in the spectrum to the best of our ability. And ultimately what that gives you is the model parameters that you need to calculate the gas mass. So the column density and a model flux. So you can compare your total luminosity to a model flux, gives you the area of all your emitting gas, times the amount of depth that you're looking through, gives you the mass of those gas clouds. We can then use that to convert our O3 image into basically a mass image, and from there combine it with the velocities to get the mass outflow rates and the energy outflow rates. So this is an example of some of the results that we found in recent years for some of these targets. We're looking at the gas mass and the kinetic energy on the left side and their outflow rates in the top right. And really the kind of key 3 takeaways I want you to take is that there's a lot of radial variation here in these parameters. And we're looking at kind of hundreds to a few kiloparsec scales here. All of these radial variations would fit within an SDSS fiber. So all of this radial variation that we're seeing is lost when we have a global measurement of these outflows. In addition, we see that the total amount of mass in the outflow, the peak outflow rate, and how far that outflow rate occurs are correlated with the AGN luminosity. So we're able to get a really detailed measure of not only how much material there is, but where it's being evacuated from most effectively and how much. So maybe you don't want to spend your entire dissertation doing 6 galaxies, right? So maybe we can find something in the middle. So maybe you don't have huge wavelength coverage with really high signal to noise. Can we find something in the middle that gives us a reasonably good estimate that you can apply to other targets? And so one of the things we started looking at is, well, how can we simplify this process down? Now, ultimately, what we want to do is convert the observed luminosity to a mass. That is the fundamental thing that we are trying to gain. So really what it comes down to is, what is the gas density? The density controls how much light you're getting per unit mass. Let's skip this one bit and show an example of some of our multi-component model results for NGC 4151 on the left and Markarian 78 on the right. So the galaxy on the left, you're looking at kind of tens to hundreds of parsec scale outflows, while the galaxy on the right is more powerful. You're looking at several hundred parsec to kiloparsec scale outflows. So these are the densities that we got from our multi-component cloudy models. We have this kind of low, medium, and high ionization that's reproducing that wide array of emission lines. And kind of the first takeaway here that we're using this as our gold standard is we see roughly 6 orders of magnitude variation in density between different components and as a function of radius. So we have this huge range in density as we move out and we propagate along the outflows. So in our 2022 paper, we did a lot of investigations as to comparing this to what would we get if we had less information. So a common assumption is using constant densities at various values, say 10 to the 2, 10 to the 3, 10 to the 4. Shocker, those tend to overestimate things quite a bit because we have a lot higher densities in the nucleus, which means we have a lot less mass per unit light. We also looked at using the common sulfur-2 doublet. Sulfur-2 is sensitive over a fairly narrow range of density, which means you're always going to get a density of about, say, 10 to the 2.5 to 10 to the 3.5. Doesn't necessarily mean that it's tracing the bulk, the bulk mass of the outflow itself. So it works well in some locations, but maybe not quite as well in others. We also investigated a couple other types of things like power law density profiles, et cetera. I encourage you to go check out the paper for that. But really the key takeaway here is we started to look at how much mass is in each of these components. The low ionization component, the highest density, so it's emitting a lot of light very efficiently with very little mass. And so it turns out that there's not generally a huge amount of mass in that component. The high ionization component, it can contribute significantly, but it tends to be much more diffuse. You don't necessarily have really strong high ionization lines to constrain it tightly depending on the quality of the data. And so we really focused in on kind of this medium ionization component, which is very well traced by things like oxygen 3. And so the question is, if we basically reduce our entire analysis from this multi-component approach with dozens of emission lines to just a single component model based on a single line ratio like O3 to H beta, can we reproduce the results? And the answer turned out to be yes, with some uncertainty within, say, factors of 3 to 4, as compared to orders of magnitude systematic uncertainties in global outflow rates. And so just to highlight how you could apply this to your favorite AGN. So first thing you want to do is to use spatially resolved spectra to determine the gas outflow velocity at each point. Drop the geometric model for how that material is traveling along your line of sight. Use that to determine your outflow velocity. Next, you want to measure an ionization-sensitive emission line ratio, such as O3 to H beta. It's not very sensitive over a big range of density or a big range of metallicity, so it's very useful. Then you want to generate cloudy models with a radial density profile to match those line ratios. I'll talk about that in a second. And this is really the key point. For AGN ionized gas, where basically all of your ionizing flux is coming from the center, this breaks the degeneracy between density and ionization parameter. The density is proportional to your total ionizing flux over the ionization parameter and then distance squared. So if you pick an ionization parameter to match your line ratio, the density is fixed. They have to vary in lockstep. So it takes a huge parameter space and makes it a line. The beauty there is if you're modeling long slit data or you're modeling IFU, you're still running the same amount of models. Anything you run for a given radius can apply to all other radii. It may not be the same best fit model, but it's physically consistent. You can draw from the same grid of models. And you can use that to calculate your mass outflow energetics. So just to wrap up here, an example that we did for 6 more galaxies. You're looking at the O3 to H beta ratios for a bunch of galaxies over the scales of several hundred parsecs. We can see that some of them are relatively constant, some of them vary quite a bit. You can use your favorite grid of cloudy models and you can convert that into a rough log U value, and then use that log U value to solve for the density at each radius. Now, there is a slight density dependence. There's a little bit of iteration here, but you can pretty quickly converge on a radial density profile shown here for some of these galaxies. And we see they're very, relatively high density in the center, tapering off quite a bit, again, spanning something like 4 orders of magnitude as we move across. So there's more results for those in the paper. I want to just go ahead and wrap up by hoping that I convince you that the spatially resolved measurements are really critical. And in my view, one of the single most important aspects is understanding the range and densities for these outflows as we move out as a function of radius. And so kind of in keeping with the theme of our discussion here, some of the things that I'd like to think moving forward, things that we might want to tackle. We need more studies of the very highly ionized X-ray gas. There was a really nice talk yesterday by FAU about using footprint lines, these really high ionization lines that are formed in X-ray gas that they emit in the optical and near infrared. So you can ultimately use James Webb as an X-ray IFU, which is kind of a cool concept. There's all sorts of additional metrics we could use to characterize what we mean when we say effective feedback. In addition to looking at outflows, I'd really like to look at just the extended hot ionized gas that's maybe not being blown out, but it's being kept hot. So we're keeping the galaxy on a boilerplate so it can't necessarily form stars. And then I think there's a lot of great discussion to be had about future synergies between our space-based telescopes, which give us unique wavelength range coverage, and really large aperture ground-based AO, which is starting to give us really high spatial resolution optical IFUs. And with that, happy to take any questions.
Well, is there any question from audience?
Thank you. That was a really nice presentation, and my direction is complexity. I'm curious how column density figures into this exercise. How critical is it to know it? And the gas hidden from us because it's the deep layers that we have.
Yeah, it's a great question. So folks online, the question is essentially what role does column density play in this, and how can we be sure that we have a good constraint on that? So that is certainly a caveat. Underlying this is that this is the ionized gas component. So there may be a larger neutral gas column behind that we can't tightly constrain. Of course, the molecular gas is separate. When we're doing the multi-component analysis, we can actually get a fairly tight constraint on the column density because we have that large variation between neutral and very highly ionized lines. So certain sets of those lines are very sensitive to the column density. So you can run your simulation and let it continue to accumulate gas until basically you've built up those key lines that are sensitive to the column density. When you're doing a single component model, you have much less constraint because you're using, say, just O theta H beta. In general, you basically just let the model kind of run until it starts to become more partially ionized, kind of, the default stopping criteria of, say, 4,000, 3,000 K. The column could be bigger than that, but that's kind of our limit that we can put on.
Great talk, Justin from Georgia State. The extent of the outflows you said was correlated highly with the AGN luminosity, right? I would assume that it would also depend on the inclination of the AGN, where the outflows would have an easier time getting to farther distances without crashing into a bunch of what Dr. Binney said yesterday, filthy gas. Has there ever been a study about any sort of correlation between AGN inclination and outflow extent?
Yeah, certainly. So there's been a number of those by Travis Fisher and others. I think the thing I kind of swept under the rug here is I did all type 2 AGN because the broadline region is pesky for me, unlike all the talks we heard yesterday where everyone needs the broadline region. So in general, these systems are kind of more oriented into the host galaxy disk. In a lot of cases, you can really see these ionized, lit up, basically molecular gas lanes as the radiation is kind of intercepting the disk, at least to some fraction. Of course, in type 1s, you have a different sort of orientation and you may be getting less impact on the disk. So there is some leeway between kind of luminosity and extent of the outflow, but on the whole, there's still a general correlation.
So this time we'll have to go into the next speaker. Yes.
Good morning. My name is Tiffany Lewis. I'm working at Michigan Tech. I lead a group that is working on theoretical development and theoretical analysis of blazars. I also work with the STScI community and I'm involved in a number of mission concept development. So for STScI, that's the Future Innovations in Gamma Ray Science Analysis group. You can see my co-chairs in this group here. The QR code is how you would join the listserv. I also have stickers with it on the back. So our goal is to review the current state of the field and to provide scientific justification for a roadmap of future missions and technology development in the gamma rays. So our driving science cases include nucleosynthesis, that's specifically about line tracing in nickel 56, which is it's a tracer of the it's a tracer of the engine for quark-flap supernovae. We're also looking at pulsar timing arrays, which help to trace supermassive black hole mergers, dark matter, gamma ray bursts, and blazars. So blazars are, of course, an indication for supermassive black hole growth and evolution. For blazars specifically, these are jetted active galaxies with one jet pointed towards Earth. These are the majority of sources in the X-rays and gamma rays. So they're going to emit at wavelengths from radio through TeV gamma rays, depending on the exact source type. And you can see sort of the range of different types of blazars that we see in the blazar spectrum. So at lower energies, sometimes up to X-rays, the dominant jet emission mechanism is going to be electron synchrotron. That's something that we know pretty well. At higher energies, from about X-rays up to MAV, sometimes TeV gamma rays, we're expecting synchrotron self-coupling. There is also evidence for external inverse Compton or alternatively photopion interactions. And in the higher energy regime, it is much less clear exactly what that emission mechanism is. Historically, blazar types were categorized according to optical observation. Those don't perfectly map onto the high energy behaviors. So I wanted to emphasize a little bit of the GeV discoveries. These are mostly coming from Fermi-Lat. The fourth Fermi-Lat AGN catalog is the largest catalog of gamma ray detected AGN. It has 3,400 sources. Most of those are blazars, some of them are Sieverts. Fermi-Lat discovered the 5 most distant gamma ray blazars. Those have redshifts around 3 and 4. The long-term Fermi-Lat light curves for a small number of blazars hint at periodic variations, and we're just starting to get those indications in the last few years. So these are periodicities that are taking more than a year in most cases. The Fermi-Lat provided GeV co-detection with IQ for Texas 0506 plus 056, the multi-messenger flare that happened in 2017. Then digging into its archival data, we also found another one in 2012. These discoveries are enabled by bringing together high effective area. Fermi's effective area is a little more than 8,000 centimeters squared with continuous all-spin monitoring. Blazars, as I mentioned, are originally categorized according to their optical properties. So the lower frequency bump in the broadband SED is due to electron synchrotron, and SSC is expected at higher energies, in this case in the X-rays, but some for high synchrotron peaked objects, it can also occur in the gamma rays. There's evidence supporting external inverse Compton for the low synchrotron cases. Photohydronic processes may also contribute to higher energy emission. Constraining whether you have Compton processes or photohydronic processes with the SEDs alone is not looking like it's very promising as an avenue of study. We still do it. It's still a lot of the papers that we put out, but we're not really coming to consensus by doing that. In the low synchrotron peaked blazars, there's a spectral break, so that's why I have this figure here. It occurs roughly in the MEV range where we haven't had detectors in a really long time. Comtel deorbited in 2001, and it was not sensitive enough to get to this MEV break. So having more sensitive MEV instrumentation would hopefully be able to verify that for us. We have tried it, but they just don't have their limits. I also wanted to mention multi-messenger searches. So in 2017, Fermi-Lat co-detected the blazar flare for with ICE for Texas 0506 plus 056. From the archives of both survey instruments, we were able to find another neutrino flare in 2012. Discussions about the origins of those neutrinos have taken several turns without really reaching a consensus. We thought, oh, maybe jets. And then for a while, it was maybe they're coming from the Krennic because we saw NGC 1068 as well. And now we're sort of back at the point where we think it's probably coming from jets, but we're not really sure how those neutrinos are made. There are about 20 additional subthreshold neutrino blazars in the IceCube dataset, depending on exactly who you talk to and how they put together their list. Neutrino spectra from blazars are usually harder than neutrino spectra from Sieverts. So that's why we do think that there is a different emission mechanism for the blazars. So to summarize kind of the areas of study that we're interested in from the gamma ray side, the big question, of course, is electronic versus hadronic jets. And that's not just a question by itself. It really points back to how the jets form, how are they powered, and which particles are accelerated for cosmic ray purposes. The way that we would probably be able to figure that out in the nearest term is by having access to MEV polarization, which means we need really high effective area in the MEV. Because when you get polarization for free when you're doing Compton reconstruction, but it splits up the data so much that you need a lot of photons. And of course, in the gamma rays where photons start. So we're also interested in high redshift blazars, in particular moving that Compton peak into the MEV range. And that points back to formation and evolution of supermassive black holes. It's also good for studying the extragalactic background light, which traces early star formation. For that, we need the MEV spectrum, just really high effective area. And of course, we're also interested in periodicity of light curves. So these instrumental requirements are complementary with multi-wavelength and multi-messenger collaboration. I wanted to point to a specific opportunity coming up. COSI is the Compton Spectrometer and Imager scheduled to launch in 2027. I believe we are still on schedule. It's going to detect gamma ray polarization, measure polarization of several lasers. We think that we're going to be able to detect about 5 lasers, probably across 30 flares. So this is not going to give us a population study, but it is going to give us a hint about science that could come from a larger mission later down the line. If you're interested in working with COSI simulations, we have currently implemented a source objector. So if you have a simulated spectrum that you want to see what it would look like in COSI's instrumentation, there's a way that you can access that. The code is all publicly available, and you should be able to just plug in your spectrum. So a lot of this is pointing towards the MEV gap. You may be familiar with the fact that most instrumentation below the gamma rays is using the photoelectric effect. One of the challenges that we have in going towards the gamma rays is that we can't use the photoelectric effect anymore. So essentially all of our photons are acting like particles, and all of our detectors have to be particle detectors. So as we're moving into the Compton scattering regime, we're starting to gain things like polarization with our spectrum, but it's really difficult to launch enough gas in the current funding regime in order to get the number of photons that we need into the detector. So you can see sort of in the salmon color there, COSI is going to push this down a little bit below where the Compton mission was. And mind you, we have not had an MEV mission in 25 years. There are also some plots or some lines on this plot that are for Amigo and Amigo X. Those are push things down further. There are other mission concepts that are large, like Gamma, TPC, and grams. I didn't have lines for them when I made this plot like 5 years ago. In the purple, in the pair creation regime, we have the Fermi lat. That's the only thing that is currently flying. And the MEV and GEV ranges, those are only accessible from space because our atmosphere changes them. And then when you get to even higher energies, you have the Cherenkov range. So the large number of lines that are sort of all overlapping is imaging atmospheric Cherenkov telescopes. And then above that, you have the water Cherenkov telescopes. So I wanted to mention another facility that I'm involved in proposing, which is the Southern Wide Field Gamma Ray Observatory. This is actually a picture of our space. And you can also see that we have some schematics for how the water tanks are going to be put together, how the detectors are going to be integrated into the water tanks. We have this sort of dual layer system that we didn't have with HAWK. We do have a lot of heritage from the HAWK Observatory. A lot of the same people are involved. A big difference is going to be the higher sensitivity and also a completely different field of view. So inside of the white dashed lines is what is excluded from the HAWK field of view, and what is in color is what would be visible to SWGO. That's just because of the location difference. And so a lot of the focus of SWGO is going to be on galactic science because we're resolving the galactic center. But we do have quite a different view of the extragalactic sky as well. You might be familiar with the fact that HAWK only really regularly observes 2 blazars, the Mercurian 421 and Mercurian 501. Happenstance of location. If we go to the southern hemisphere, all of a sudden we have like 30 blazars at our disposal that we should be able to regularly observe. And some of the brighter ones have been names on this plot. So just in summary, Fermi Lat is a probe-class GEV mission. It launched in 2008. It's been a workhorse both for intrinsically GEV science as well as multi-wavelength quasar research. Fermi Lat's wide field of view enables it to serve as a flare alert platform for other wavelengths, and its data archive is a profound legacy for long cadence phenomena and things that we didn't initially know to look for. Over a decade of GEV monitoring has clarified and refined questions that need to be answered with a different set of tools. A high effective area MEV mission would address most of those outstanding questions, and ground-based TEV instrumentation lets us use quasars to contribute to more fundamental work on cosmic ray acceleration and extragalactic background. I can stop there.
Thank you, Tiffany. So now, okay, we have plenty of time for questions.
Hi, thank you for the nice talk. I was curious on your multi-messenger point there. Do any of these sources overlap with the previous Kepler blazars, or will they be in fields that'll be kind of the Roman Rubin time series observations, or are some of these even bright enough that, when you have a trigger event, they can be followed up with smaller ground-based scopes like, the advanced AAS247 network or something like that?
So these sources or?
Yeah, sure. Start with those.
So these are all in the southern hemisphere. I think, wasn't Kepler pointing more towards like a northern constellation? I don't know that there would be a lot of overlap there, but I could double check.
Okay, is there any other questions? Or online? Is there any online question from? Oh, sorry.
Thank you. I'm Tiffany from Mora. At some point in your talk, and I think I missed a piece of it, I want to ask you to discuss a bit more. You said that there may be more differences between blazars and Seiferts besides the orientation of the jet. Can you? Yeah, I think I missed.
Yeah,
Elaborate on
yes.
this?
Usually, the way that I would usually specify AGN secrets would be mostly unjetted, and then there are jetted active galaxies. Within jetted active galaxies, blazars are the ones with the jet that's pointing towards Earth. So a lot of what we study with blazars is actually the jet itself. It's so Doppler boosted, it usually outshines the galaxy behind it by quite a lot. It will outshine a lot of the detail. So we don't usually study the host galaxy for blazars, and when you look at the spectrum for a blazar, you don't actually have galaxy in it. So you get a little bit of accretion disk in the UV and that's about it from the host galaxy.
Okay, maybe I can ask, so I'm part of the RESI Galaxies Specific Instrument, so we get lots of optical spectra and we do get lots of blazars, kind of, this just happens.
Yeah.
Some of them we do see a bit of host, we can get a redshift, and some of them we don't see anything, so we can't get a redshift. So one question I have, which is a quick follow-up, but is it common to see a blazar with the Mercury absorption? Because we have like redshift 0 absorption features on top of the blazar.
Well, I mean, I don't usually work with data because of years, so I will put that caveat out there first. I usually rely on other people for that. But my expectation is if you're looking through a significant amount of Milky Way, then you would probably have Milky Way in your spectrum, right?
Yeah. Okay. Yeah, I think that's what we're saying. Thank you.
So we can go into the next speaker. So thank you, Tiffany.
So very unfortunate. Smell them. Smell them.
Okay. Good morning, everybody. I'm Jianwei, I'm an assistant research professor from the University of Arizona. It's my great pleasure to take this opportunity to give you some updates on the high-redshift obscure aging study with JWST and MIRI. So why we should hear about the obscure aging population? I think the one sentence summary is obscuration is intrinsically associated with the growth and the evolution of massive black holes. So as this cartoon shows, whether the aging is triggered by secular gas-rich mergers of circular interactions in the early phase of black hole growth, the nuclear region is expected to be heavily obscured. And later on, the system would be powerful enough, so there is a blowout phase, which ends up with an unobscured quasar. So this talk will focus on this part, where the system is heavily obscured. So as you may expect, due to heavy obscuration, such systems are very hard to identify. So before the launch of JWST this task force, we have conducted a comprehensive search of agent population using the deepest X-ray radio and Switzer medium fry data in the blue south field. And we reached the conclusion is actually that no one single method of selection of wavelengths can come close to select a complete agent sensor. So it's like the story of an elephant and the man. You have to combine all the efforts from different angles to reach a complete picture. So the situation was summarized nicely in the actual 2020 report. So what we know is there definitely a large population of field agents, but how this population depends on the galaxy property environment are hardly known. And the lack of complete sensors is a major obstacle to our complete picture of supermassive black holes and its relation with the host system. And to resolve this problem, the MIRI science team in the US have proposed a GTO program called SMELT. So we have targeted the central region of the good south field with 8 MIRI bands covering observing from 5 to 26 micron. So as you know, this field has been extensively covered by the near-time data from JWST as well as our programs, as well as near-spec of spectroscopic follow-up. And you may also realize this field has been previously extended observed by Chandra, VLA, and HST. So this is the best place to benchmark the performance of MIRI agent selection. And I want to mention the data from this program. The MIRI imaging catalog as well as near-spec observations have all been released. You can just search online, you will find the data to play it. And taking advantage of different spectral energy distribution between dark-forming galaxies and AGN, we have proposed some semi-empirical SD model to select agents across the field. And what we found is that actually, although the MIRI survey is relatively shallow, so combined 8 bands, each pointing only have slightly over 2 hour exposure time. It has yielded 2.4 times more agent than the Chandra deep south field. That's actually an exposure time around 800 hours. And about 80 of the MIRI agents are the first time discoveries. And it starts showing the overlap of our MIRI agent sample with a free-GWT agent sample, which we did a search from X-ray to radio, as well as CDF South agent catalog. So you can see that actually the overlap is not that huge. Okay. So definitely we are proving a new parameter space. And also we have conducted some near-spec spectroscopic follow-ups. So these are some agent sample with near-spec rastering optical coverage. So you can see from the classical PPT diagram, most of these MIRI agents in red cannot be identified as agent as standard optical narrow agent. And here are 3 example spectrum of these 3 systems in the AGN region. So you can see they show very obvious evidence of inflow, outflow. That means the system are disturbed. Okay. We also took a look at their galaxy morphology with near-time imaging. So what we plot here is basically, as I mentioned, most MIRI agents are not detected as Chandra deep data, but we can assume they are just counting things. Okay, and we classify the sample by different morphology classes with corresponding expected accurate column density. So you can see the MIRI agent actually dominated the irregular peculiar morphology as well as some merger systems. So again, we confirm that most of the MIRI agents, as opposed to known, have merger of this curve morphology, which is consistent with the standard pictures that the agent may be triggered by the gas-rich mergers, which will be very dusty, that can be only seen in the medium frame. And moving to even high-redshift, we know that the JWST has made a lot of progress. We mastered some very peculiar population called little red dot. They were identified, selected mainly by the near-time colors, and some spectroscopic follow-up found that many of them may have brown lines. So some people argue they may be Asian, but there are some disagreements from some other communities, so the nature is still under debate. And also based on some standard optical or UV
spectroscopic diagnostic, people have identified some brown light agents as shown in these papers, as well as people relied on some Raspberry UV diagnostic or some very high ionized emission lines. People identify some standard narrow light agents. Okay, all these results are wonderful, but I want to point out actually not all agents can be found at observed frame less than 5 microns from either near CAM or near SPEC. So we need to move to even longer wavelengths with MIRI to say what's the obscured population or dusty population in the relative early universe. Okay. So besides the smells data I have mentioned previously, which have H1, we also have some very deep MIRI imaging at 7 red frame, observed frame 7.7 micron in small regions, which have an exposure time in one band over 40 hours. So it's pretty deep. And actually, we have detection of the MIRI flux for redshift 13 Galaxies. So we can use this data set to search for high redshift obscured AGN to say how far we can go with the existing MIRI data. So regarding the selection technique, this just show you an example. So this is known as the low metallicity brown light agent at redshift about 5.6. And we have a very clear MIRI detection at observed frame 7.7 micron. So again, we use the same empirical ST selection technique. So in this case, although we only have one data point, we can make some speculation that whether this excess emission is due to star emission or agent activity by combining the data from the radio and the alpha. So we can confirm that this solution, this agent solution, is unique. And also sometimes we will combine the morphology information from this MIRI imaging just because the dust emission from the agent will be a point-like source end result. So by combining these two correct selection criterion, we end up about 18 MIRI agent candidates with different level of confidence. And they span the redshift from 4 to 9 with 18 barometric nerve from 10 to the 9 to 10 to the 12. Solid luminosity hosted by host gases with stellar mass from 10 to the 8 to 10 to the 11 solar masses. And on the right panel, I just show you the stack as is of our MIRI agent candidates, which shown as red dots, and the little red dot sample over the same sky footprint. So you can say the little red dot population is consistent with the previous study that they generally lack of strong hot dust emission. But our MIRI agent, by selection, they are relatively luminous in the MIRI band, almost all the MIRI band. So clearly, they are just two different populations. Okay. And these are some footprint plot of different agent population identified previously over the sky. And here I just show you the Venn diagram to show you the intersections between the little red dot population and some brown light agent population found by the near spectroscopic collapse, as well as our MIRI agent population. So you can see again the identification, the overlap is actually small. So I want to highlight that almost all the brown light agents, once they have enough MIRI detection, we can safely identify as a dusty agent. So that's something that some people may not have some different arguments, but that's something I want to get. And also we have some near-sky follow-up observation from the JWST archive. And again, I want to highlight that most of these high-redshift MIRI agents cannot be identified by some standard agent selection criterion in the Raspberry optical, meaning the system is heavily obscured. And we also made some crude estimation of brown light agent fraction. It's about 20%. It's also consistent with what we got from the cosmic zone. And some agents have some relatively strong evidence of outflow, but this will be reported in another work in the future. And regarding their multi-wavelength detection, it's consistent with other high redshift agent populations. They are actually weak. We did the second analysis of all the 68 actually without actually MIRI agent without accurate detection, we do not see any signals. And also ALMA, which is detecting, there is no detection as well. Okay. And we also took take a look at the morphology. About 80 MIRI agents actually hosted in merger or disturbed morphology. Is consistent with some pictures of early supermassive level buildup, which the system would be very turbulent. And also regarding the gas environment, we found clear evidence that this MIRI agent prefers to live in gassy or overdense environment, while the little red dots seems to not live in an overdense or underdense environment. They are consistent with the field. And this is a quick summary. So the key message is GenSiG MIRI is very powerful to search for dust obscured agent across the cosmic time. And the MIRI agent population is very different from the little red dot population with very well sprouted as I listed here. And regarding the future, I think definitely we need more large aerial and multi-band MIRI imaging like the SMELL program. And Prima in the far infrared will be the key if you want to know even higher redshift. And definitely we can combine with other live surveys from Roman, Robin, or Phoenix to understand what's the MIRI agent population around the general gassy population. Also, there are some next generation multi-valence probes will be very helpful. Yeah. I will just stop here and save some time for that. Thank you.
Thank you, Jianwei. So is there any question from the audience?
Thanks so much for this. This is really exciting. I'm Ryan from Dartmouth College. Given that these things are super X-ray weak, and there's so many of them that are, when you stack them, are ones that are not detected in the deep under observation for that converting one, can you speak to what fraction of these may be conflict? Because as you know, that's been sort of a big question. How many of them are really, how many AGN in the whole, cosmic population are really heavily obscured? And I think we could get a really good constraint.
Yeah, I think the crude estimation is about 80%. And actually previously we did some study on how the obscuration fraction evolve with redshift. So above redshift 4 is just like 80%. That's the lower limit actually. And I also I would think it's 60%. So you will see the obscured aging fraction increases with the redshift.
Right. Would that be the obscured fraction or actually would that be the obscured fraction or actually the Compton thick fraction, the ones that are over 10 to the 24?
Actually, I'm not sure because there are some pictures arguing that high redshift, the corona component may not exist.
Right.
In some low magnitude environments.
Right. Okay, that makes it hard. Yeah. Thanks.
Any question from audience? Still have time. So any question? Okay. So maybe I have one question about, you mentioned about a simulated dark, it means there's no cold gas. But like, do you think when they forming that obscure agent, they just don't, they're just heating the cold gas to the warmer gas, or the gas still, I mean, just like the gas still there, but the temperature just different. Because in a high redshift, like the intensity mapping, we are using the cold CO shifting. So absolutely, in the high redshift, we have that cold gas. So do you have any comment about this?
Yeah, I think you have to spend a lot of explore time to detect any gas component because compared to like red quasars, they are much fainter in the sub-meter band. And actually, I do not know. I didn't realize any follow-up program of this. There were also any gas emission from this high redshift region.
Okay. So probably we can go into the next sections. So next section will be more interactive.
Stop presentation.
Yes. Oh, okay. So now is the new interactive discussions. So this year we start the mirror group suggested by Fabio. So this is the interactive board, and you can access from online. If you have laptop, just type this short URL, or if you already have the cell phone, you can go into to scan the QR code and access the board. And this is the area we want to collect everyone's ideas for the next 10 to 20 years development about vision agent science. So we have some sample about this. Is what's the science questions we are now discussable, traceable, and we need to like teaching, scaling, and standardize. I think the standardize is very important. So we try this some samples so we can get inspired if you have any questions. So like for me, I would say, we have different names for the agent, like the students always ask me what is the neuroline agent, proline agent, type 1 agent, type 2 agents. When the students study this, they're always confused about it. So this is kind of questions. And also like what is the key questions that remain unanswered for the new telescope, like time domain telescope, like grouping, and the task is already there, and OFC, and even a future like the LISA telescope. So the gravitational. So there are any ideas about the time domain series can be discussed in this block. And like me, from my question is like agent candidates. Agent time domain usually talking about the geometry, but how can we separate it as the geometry, or it is just the agent event, X-ray, like the X-ray event, agent event. And also like the AI, because now we know that AI is very popular. Well, even the A and B hosts can be an AI. So I would say the AI is very powerful right now. So how the AI can help us to help the agent science? Like, is this possible? Well, we already know the machine learning will pick some agent type from the large data set, but what is the okay? My background is like software engineer, so I was thinking about like a quality assurance, how we import the quality assurance to justify those AGN from the AI selected AGN. And also the last part is anything here we didn't discuss, but you want to know, you have a question, and even you have some direction you want to listen these directions in the future talk, you also can post in this area. This area is free. If you have any comments, you can leave there. So I stop here, and now we have about 10 minutes we can discuss to each other inside this group. Yeah, inside this group. So if this is the electronic, and if you prefer the very old fashioned, we still have a physical real whiteboard in here. So, and even we have the pens. So the RGB color pens is also included. So if you can pick which one you would like to, give your idea about the agent science community.
I'll just also mention for the online folks, we're going to mute you on our side so you guys can have your discussion. Just come through, you guys decide to go to breakout rooms if you like. For those in the room, something I failed to mention before, while we're looking towards the debate survey and how should our community start preparing for those discussions, we're also going to use what we hear from you in this discussion to help shape what we're going to talk about next series for the coming year. So please think big and get those ideas down, and then we'll talk. We'll let you guys talk amongst yourselves and other things in the mirror board for 10-15 minutes to see how it's going. and as a larger group can put things together. Thanks.
All right. I'm gonna mute the room so they can't hear it. Oh, now we can't hear them. Um, and then I don't know if do we want to share Pallavi like a route?
Should I share the slide or the mirror board?
I get the slide is already on the screen. So hopefully, are people able to? Oh, now it's gone.
Oh, okay.
But
I think Erin is talking to us,
oh,
but we can't hear her.
dang.
No. Erin, you're muted if you're talking to us.
Now I'm talking and I'm singing and all right, I'm gonna just presume that they're gonna be talking on their own.
Fine, yeah. Okay.
Yeah. Oh, here's Aaron. Okay.
Maybe they're muted, but they're hearing us talk. Maybe that's a possibility in the room. Is that what's happening?
Maybe.
Give me a thumbs up if we are disturbing or no. Yeah, I think that's what they're figuring out.
Hi. I thought that we were gonna go in a separate talk here privately. So we muted you guys. Mingy, can you hear me?
Yes, now we can hear you.
Okay, but I muted you guys so that we could be in this room or try to get people talking over
I
here.
think if we just turn our volume down on this side, then we won't hear you. At least that's how it was working. So
Okay.
I think we're good. We can control it on this side. We'll bring your volume back up and let you know that we're listening.
So we're not going to mute you guys?
You can mute us and we will turn your volume down. That way we have separation.
Great.
I think this is fine now.
Okay.
Is this good?
This sounds good. They can't hear us, and I don't think they're looking at us anymore.
Great.
So now it's fine. Goodbye. Go away. All right. Enrique, I see that you're hearing me, except the main room now that it's muted. So yeah, I think that this conversation is just for folks online.
Right.
So if you're online and you're available to talk, yep.
Hey.
Oh, I see you. Hey, man.
Yeah, perfect. Hey, how's it going?
So
nobody,
well,
so we are not in like being here in the main room, right?
that is my understanding is that it
Okay,
is,
perfect. Yeah, this is
yes.
I didn't want to talk because it's not gonna be like.
Yeah. No. So it's just us now talking, but you can see there's lots of little bees on
Yes.
this Miro board now. So, I mean, I think it'd be really, yeah, it's be constructive for us to just talk about some ideas that we have. But I mean, you can also, you're welcome to just put down little sticky notes about different ideas that you have for the future of AGN science. So specifically, I put one down in the upper left quadrant that I think it's important that we start with all the data that we have available to start or consistently be combining the different phases in our analyses because we're still only in one-track minds of this is radio data or this is X-ray data. And so that's, I think, leading to misinterpretations still. So with the amount of data that's in the archive, in all of the archives, I think it's imperative that we start combining them consistently then. So,
Yeah, I agree with that. So like, I like the multi-wavelength, but also I think needs similar resolution scales too, right? Because sometimes,
Right. Yeah.
yeah, sometimes we have like very poor resolution but very high, and it's very complicated to do a multi-analysis, multi-wavelength analysis that way.
Yeah, that sounds like a great thing to go in the upper right quadrant because it's like, what questions are going to be unanswered? Well, we can't answer some of these questions, even if we are doing a multi-wavelength analysis, unless we're having those similar resolutions. So I think that if you wanted to put like a sticky note there,
What do
like,
you see is in what key questions would remain
uh,
answered, or which
yeah,
one?
without
Okay.
new missions, what
Oh,
capabilities are missing, right? So if we say we want to have everything be at the
oh,
same resolution, then it would be, I think that's really
oh.
critical to us understanding.
Okay, I still don't understand this thing, but I will
So we got
try.
these little sticky notes up in the
Okay,
upper
now
right
I got
corner,
it.
so
Yeah.
you can grab
Got
one.
it, got it, got it, got it, got
I
Boom.
think I just created one. Okay, and for you,
it. Okay.
Enrique, if you want, can you see that? Never mind. It's fine. You got it.
Whoa. Okay. Oh, I don't know what is. I don't know what I'm doing.
I think it's working.
Yep.
Okay. Okay.
Perfect.
Oh, why I have two? Oh no.
No, no, I
I
just
just
put
see
it.
your first note.
All right. Oh, they're here.
Um, yeah, so but I concur. Like we need to get everything down to like X-rays. It's still hard with 1 arc second resolution with Chandra, so we have a lot of room to expand there. Um, who else is online that has potentially some ideas? Raga, hi.
Hi, I'm thinking about like dwarf galaxies and how they place in the AGN verse, and then basically AGN in dwarf galaxies and how it can be compared with massive galaxies, and also with like star forming galaxies in the low mass regime.
Yeah. So maybe that feels like an upper left quadrant situation where we're with the existing facilities that we have. I mean, it's always
Yeah.
important to go for the full range of scale. And I know, and I'm proposing, we're always like, we need the biggest, brightest ones because they're the easiest to observe. But it is important to then focus on the smaller ones too to understand where things aren't important necessarily anymore, like different feedback processes, um, and how they differ along different scales. So I think that that's a great idea, for it to be including in here.
How do I edit this? Sorry. Oh,
Um,
Can you edit? I
boom.
just added a note for you. Can you edit that one?
You just clicked on the whole field, Raga. So,
Just double click and see
okay,
if you
got it.
can edit.
Yeah.
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 Yeah, I just added a note so that you can feel free to edit it as you like.
Oh, we
Right.
need to put our name at the beginning.
Don't have to, but I mean, it's convenient. Some, I mean, make your mark, man. Let people know that, like,
If it's related with big field, you know it's me.
yeah. So, I don't know. Yeah, what are we not talking about yet? What did you put in your role of magnetic fields? Yeah, dude.
Yes.
I mean, I think we're slowly coming online for that. I'm gonna grab a dot. Can I grab one? I think so. And no, how do I not pan? Pointer. I think I can grab like a little dot and put it here to be like +1. Boom.
Oh, I think you can react, Travis, back up.
Oh, oh,
I think
yeah.
someone just did for Enrique's one note. So I think you can do that. or here? Like,
Yeah, I just put a dot there. Oh, see, I just did a thumbs up at the bottom. That's weird. No, I don't want that.
see, you can select fire as well.
Oh, cool.
Or
Ah,
some emoji.
yeah. Thumbs up. Ow. Cool. Oh, that's convenient.
Oh, ha! You can do a fire. Nice. I like it.
Yeah.
Yeah, so many cursors moving is a little distracting though. It's
Yeah.
hard
Lots
to
of
find your own cursor.
lots of little bees.
Interesting parentalability. Okay. Oh, we are always assuming that it's Milky Way dust still work at high redshift,
Mm.
which I don't think is the same dust composition. Or should we expect
Reddening,
to
you
have the
mean?
same? Hmm?
Like reddening?
Yeah, the dust composition, like chemical composition. So we are always assuming the same, yeah, chemical, like the same reddening laws
Oh, yeah,
as the
I
Milky
think
Way for AGN, which is not.
yeah.
Oh, should not be. I
Marcia
don't know.
was asking in chat from Mitch's talk, like, what are the different dust models and metallicities and how do they add uncertainties to these results?
Yeah.
So I'll put that in.
Oh.
What did that sound mean?
Oh, that was for if someone leaves the meeting.
Oh, sad. How do I just make it wider? Like, Mingy made a nice wide post-it note. I want to do that.
You can
Oh,
change the size of the post-it notes, right? By going in the
oh, I figured it out. Yep, sorry. I think I drew a line last time I tried to do that, so I was discouraged. But
Mm.
Which is your problem? Oh.
while we're working on this, I guess, like, how do you guys think that this meeting, this little splinter went? Was it constructive? Is it being constructive, do you think? Any comments, thoughts?
I like these sticky notes. I don't know if you are all planning to have a short discussion or brainstorming about this, but this is very, very, very interesting because you allow the people first to put their thoughts independently of talking or not be biased.
Oh, hold on. Oh, I guess they're coming back.
Our 10 minutes over. Oh,
Oh, yeah, we only have like 10 minutes left.
oh, okay.
So now it's 10:20, so we have plenty suggestions, comments in this board. And if anyone wants to speak out in these sections, or welcome audience here to bring their ideas to us. So is there anyone want to discuss or when describe, because we have so many comments here, so we can just we can just talk in one and we already putting it. Yes. Does anyone like to share?
Do we have anybody online who would like to highlight their?
Or we can go into some thumbs up idea. Like maybe go with this one first. Any thumbs up? Oh, This is our first AGN science question. So is it?
Hey, it's Travis online, and I think that we had two complementary ideas. The first was that I was suggesting that for feedback models of AGN everywhere, we need to consistently be using a combination of multi-phase data in our analyses, and that means we should always be including as often as possible radio and optical and infrared and X-ray and all the stuff because we have all of this data on the archive now. And it behooves us to make sure that we're making sure whatever we're saying from our analyses in the waveband we like most plays well with all of the data from the other data sets. So that complements Enrique left a note then saying that, well, for what capabilities are missing in the upper right quadrant is that multi-phase analysis requires similar angular resolution. So we're still missing that in a couple different wavebands, particularly X-ray in my mind. So it'd be great to have that moving forward. And then separately, I thought that Ryan had an interesting idea of like the impact of AGN on planetary habitability. I mean, I've given some public talks where I'm like, we're probably fine. Like if Sagittarius A star pointed in our direction, I think that would be okay at this distance. But I mean, I would like to know that just for Earth specifically first, and then we could like pair with exoplanet folks to understand how survivability works in other galaxies too.
Yes.
Hi, can you hear me online?
Yes.
Okay, awesome. I just wanted to share that Sean Chen at Beijing University has done work on this. If you're interested in the literature, I don't know if you already do work on this, but just a suggestion, so it's good too. Oh, sorry, works on like the idea of like habitability in the presence of like planetary habitability in the presence of an AGN. Yeah.
Cool. Thank you.
Can I make one quick comment?
Yes, you can.
This is sort of all. That's great. I'm the one who just comment. I don't think well, I'll look at those papers, but I thought this about this because of one paper that undergrad worked on with me at Dartmouth actually that and looking at what happens to an atmosphere when you blast it to the chemical composition of an atmosphere when you blast it with an AGN UV container. And the short answer, I think there's many aspects of this, but Travis, I think that the short answer is the Earth will always be fine, pretty much. But we know of a lot of these really fast or compact galaxies where there are a lot of stars close to the black hole and very little cold gas in between them and the black hole, and those planets may really be in trouble, depending on what the AGN did, sort of the history of the AGN mission. So anyway, yes, I think this, but it's still like really early days for that field.
So now we move to the second question. This one. The second. So now we move to the second questions. So what is the key science remain unanswered without the new Prof and Explorer class missions? And what's the capability is still missing? Yes. So is there any one would like to comment this or online? Or online? Okay.
Hi there, I'm Daniel Colombo with the Black Hole Explorer mission. I'm coming at this very much from the submillimeter field beyond 5, but I'm trying to see how we can help fill in the C pieces of the puzzle. Part of that comes from horizon scale imaging. That's something that I'm actually hoping to do for more targets beyond the MIRI STScI, and trying to see what, how informative that will be for the rest of the AGN community to have some sense of masses and in some cases spins for a broader class of low luminosity AGN. So I'd love to know how useful that would be, because we're excited about it, but we're excited about everything. So just some sense of that would be great.
So I'm going to say a buzzword, X-ray corona, which is very much what I'm looking at too. Maybe we can talk afterwards. But the other thing that would be complementary is one thing that I'm looking at, trying to use theoretical models to predict, is connecting radio polarization to X-ray polarization. And we can't really do that unless we have high resolution X-ray something, right? So I think if we can reconcile the radio and the X-ray communities together somehow, right? Moonshot. But if we can do that, then that will make a really powerful science case, especially in the future.
Just to piggyback on the complementarity between radio and X-ray, I think we have some beautiful spin constraints from X-rays that we're trying to reconcile with theoretical modeling of where the spins ought to converge just from magnetically launched jets using the Butterfly static mechanism. And it's pretty hard to understand how you end up with so many highly spinning black holes without some kind of selection effect. And so I think filling that in with the low luminosity population for radio, it will help connect the dots there, and then maybe even find some interesting.
Maybe a similar, I mean, very similar to here. We're talking about different phase, different angular resolution. I know like the radio, especially the ELMA community for the AGN host galaxies, like FETs, they also have some discussion to fix how to grid the pixels. What is the bin size to grid it? So that is how they, I know the fence is, they have the rules to how to grid the pixels in the ELMA data or maybe JWST data. And I know the goals, we still in the goals team, I mean, control the luminous infrared bright object. The goals meeting also discussing this. So I think there the different matching the different spatial resolution is a very common issue problems for all the community, not only across the way, but often even within the same radio sublimiter community, we different instrument will still have the same. So we probably have to go into the third one. The third one is the AI part. So how will AI and also the large survey change the agent science and what we're concerning about something like this. So any related to AI parts are welcome. Yes.
Question. This is something we've talked a little bit about earlier, and I'm still not quite sure where to go. Like, there's been a lot of unsupervised classification with machine learning, but I think we're still at the point where it can be very difficult to interpret what you get out of that. But there are other things with machine learning you can basically speed up and make really efficient things where you already know what you're doing, but you can just make a computer do it better for you. And so I'm wondering, among the group, like, I kind of think of the applications as being one or other of those things, although I'm sure there's a mix of them. But I don't have a good sense of what the field is in terms of what people are focusing on. So I'm just curious if anybody has any experience in their own.
Any experience about yes.
So one thing that we use for is we are thinking about ways to use machine learning, so doing something that we already do very efficiently to basically make our lucky imaging better. How do you select your good frames or your good frames in the market that we get? Which we've explored it with unsupervised methods, but as you said, it's very, very hard to interpret what comes out of this. So instead, you know what you want to do and you do it well. And I think those are probably the way that we're going for a little bit longer at least until the statistics get better on us.
So maybe I can comment about AI. I know something like the JWST or Rubin, they something like do a survey. I mean, inside out survey pipeline. I remember last year, I attended a Splinter sections. They're talking about automatically classify different objects. So I don't know how the details, but it looks like the AGN is one of the objects that will be classified using an AI. So I don't know what's the detail, but this is the one implementation about AI in large survey data. And the radio data, I probably can talk about more details from my understanding. I know the Radio Institute are talking about the cleaning process can be, image reconstructed process can be performed by the AI, but it's still want to discuss. And I also have our team in Taiwan, we have some testing about implementation like visualization tools. Can we classify the spiral galaxies and elliptical galaxies? And I would say the result is almost 2 years ago, and we use commercial machine learning tools. And we found we use a commercial machine learning tools. If the image size is different, classifies just the spiral and elliptical, they still have a lot of improvement. So that is 2 years ago on our RU program we did. I'm not sure right now is there any update. So maybe we can go into the last part. If you have any thinking about this, you can talking about without this, beyond these 3 questions.
Yeah, I shared the note, so I'm with the CUNY Graduate Center. I shared the note about compact objects embedded in AGN disks. And one thing I've been thinking about in my master's thesis in general as a science interest is I think it's an interesting question to think about sort of what I would imagine as like non-traditional modes of AGN variability. That being like you have heating from like the corona, you have X-ray photons, high energy photons from the corona that can heat like the UV and optical regions of the disk. And we can sort of well model this variability through reverberation happenings and such. What I'm interested in is this idea that we have a population of compact objects embedded within the disk of an AGN or AGN generally, and I can justify this if you're curious later. What I'm interested in is how this population can contribute to sort of baseline verbal that we have in AGN, this baseline AGN variability, because these things will be turning up stuff and the disk will be interacting with each other in the disk, and how would those temperature fluctuations that they would be imposing into the disk actually sort of propagate out into maybe the photosphere and emerge as sort of contribution to AGN variability. Yeah. And also, I'm a theorist, so like, what do observation people need from us? Yeah.
Thank you.
I was just gonna say we're pushing past our time, and I know that everybody's eager, probably is to get over to the Hub Worlds session that's going on. It started at the top of the hour. So I'll just say thank you for all of these great ideas. Some of the things that I picked up on quickly is we need to maybe start breaking down those perceived barriers and wavelength and other things and make sure we bring the community together. So we'll talk about how to do that in our talks. Maybe our spotlight series, we can bring in somebody from one wavelength and from another, so we can start really having conversations about bringing our communities together and really leveraging what we're learning at each wavelength to benefit each other. And there are other many great ideas that came from this. So we will build on this, look for, can you put up our slide with the QR code again? Look for more announcements to get on the email list if you aren't on it yet. You'll find that on our website. And we will look forward to continuing the conversation and moving towards really preparing for that next decadal survey and ensuring that our ideas from our AGN community, can rise to the top to really influence what the recommendations will be coming from the decadal. Anything else I should be saying? I think we're good. Have a great rest of your meeting. Thanks for coming. Thanks for those of you online who joined, and we will look forward to seeing you all online hopefully next month. And we just got confirmation of our February vision talk. Will be Santiago Garcia Barilla. It will be February 17th, so we look forward to that as well. So thank you all. Thank you.
Right. Thanks. Thanks, everyone. I think it went well.
Yeah. Bye, everybody.
Okay.